Now that we've covered the intersection of a line and a plane, let's consider the intersection of two planes. And the cases for this are the same as we had before. The cases, case one, the planes can be parallel. They could perhaps intersect at a line, or they could be coincident. So they could actually just be scalar representations of the same plane. And the process for finding out the intersection of two planes is very similar to what we were just working with when we were finding out the intersection of two lines or two lines in a plane. So we also want these planes to be in scalar form before we begin, because we're going to be using similar to systems of equations in order to solve this. So essentially what we're going to do is we're going to look to eliminate one of the variables by adding or subtracting one line from the other. We're going to set one of the other remaining variables to t or some multiple of t at our convenience, and I'll show you what I mean when we get there. Then we're just going to solve for the other variables and write the equation in parametric or vector form. So let's begin. Let's find the intersection of these two planes, plane 1 and plane 2. All right, to begin, I'm going to identify my planes by calling them plane 1 and plane 2. And I'm going to use some type of elimination strategy to get rid of one variable. I always have a lot of options, so solutions for these types of problems can go in a variety of different ways. However, you should be arriving at the same destination because the intersection will be happening at the same point regardless of the strategy that you use to solve these. All right, so let's take plane 1 and subtract plane 2 from it. So I'm going to go 3x take away 2x is just x. Negative 2y take away 1 more y is negative 3y. And z take away z is 0, so I've eliminated that variable. 8 take away 1 is 9. And now I have eliminated a variable. Now I'm going to do this next step, which is a little bit hard to visualize, but I am going to go ahead and just say y is t. And the reason that I can do this, I can set any of my parameters to equal to t because I can just assign this value because my orientation of my plane can go in any direction of a particular axes. I can make it go in that particular direction. So for this case, I'm going to make y equal t, and then I'm going to carry on. Okay, so now that y equals t, I'm going to say that x minus 3t equals 9, and x therefore equals 9 plus 3t. Now I have an expression for y, an expression for x. I just need to find an expression for z. So I'm going to take y equals t and x equals 9 plus 3t, and I'm going to put that into an expression for the plane. I'll use the second expression, so I'm going to sub into 2. So I have 2 times x, which is 9 plus 3t, and plus y, which is t, plus z equals negative 1. Expand out my brackets, combine my like terms. I'm going to move this to the other side. Solve for z. Okay, now I have a representation for each of my parameters. So my parametric equation, my x is 9 plus 3t. My y is t, I said that. And in relation to y being t, z must be negative 19 plus 7t. There's my solution. Okay, before we continue with the video lesson, I would suggest that you go and do page 300, number 3, using this strategy, and then come back and we're going to learn another strategy. So this other strategy that we're going to talk about is called the Gauss-Jordan elimination strategy. And this is simpler. I'm going to use a matrix. And this is simpler as my systems become more and more complicated. For a simple system, it might seem like overkill, but as I look at more complicated cases, a matrix can be useful to just kind of streamline the process. So a matrix is just a representation of the coefficients in an ordered table. And then that way I'm just focusing on the mathematical operations rather than the x and y variables. So here's my 2 planes. And I'm going to create a matrix of these values by placing the coefficients in order and using a long vertical line to separate the sides of the equation. So I start with a long square bracket. 2 is the coefficient of x. -3 is the coefficient of y. 2 is the coefficient of z, equals 6. I write my other one right underneath. And this is the matrix that represents those 2 planes. I have plane 1 here, plane 2 in the second row. Now, it doesn't matter the order that I wrote them in. So I can definitely have written line 2 on top. I can even switch them halfway through this. Okay. The goal of a matrix, a reduced row echelon form, is to have the matrix in the form where I have ones on the diagonal. So in this case, I only have 2 entries, so I'm only going to create this diagonal here, this ones on the diagonal here. That means that these values in the remaining spots can just be whatever number. Okay, so this section right here is dependent, it's coming from this 2 by 2 is coming from the fact that I have 2 planes that I'm looking at. So if I had 3, then I would need to have 3, a diagonal of 3 ones. If I had 4, I'd have a diagonal of 4 ones. Okay, so in order to get to this form, I need to do 2 things. So I need to create zeros in the non-1 spots only, and then I need to reduce to 1. So let's give this a try. So I'm going to just copy our matrix down from before. So 2, -3, 2 equals 6. 1, 2, -3 is 10. Now it's super important that I track what I do so that my thinking is clear, because I'm not going to actually write down any math onto the page. So getting the zeros first. So my first goal is going to be to get a 0 into this spot here. Because I'm going to get a 0 into that spot there, I'm going to actually leave 1 as it is. And I can write that in right now as it is. Okay, in order to get a 0 into this spot, I am going to have to take 2 times 2 and subtract row 1 from it. And I'd like to try to keep my pattern of how I do this the same, and I'll just make less mistakes with that. Okay, so I'm going to go 2 times 2, 2 times row 2, subtract row 1. So I'm looking here, 2 times 1 is 2, minus 2 is 0. That's the output that I wanted. 2 times 2 is 4, minus -3 is 7. 2 times -3 is -6, minus 2 more is -8. 2 times 10 is 20, minus 6, or sorry, yeah, 14. Okay, so now I have 1, 0. So the next goal that I'm going to have is I'm going to want to get a 0 here. So in order to do that, I'm going to, let's just set up my matrix. In order to do that, in order to get -3 to become a 0 when I'm working with a 7, I'm going to take 7 times row 1 and add it to 3 times row 2. Okay. So 7 times row 1, which is 2, is 14, plus 3 times 0, which is 0, so this is 14. 7 times row 1, which is negative 3, is negative 21, plus 3 times 7 is 21, so that's a 0. And 7 times row 1, which is 2, plus 3 times row 2, which is negative 8, is going to be 14 minus 24, which is negative 10. 6 times 7 plus 3 times 14, let's do it on my calculator, and I get 84. Not going to change this second row right now, so I'll just write it back in as is. I wrote 2. Okay, now I have the zeros. Now I'm ready to get the ones in these two spots. Those two things can happen kind of in the same step. In order to get the one in the first spot, I need to divide everything by 14. So that's going to give me 14 over 14, 0 times 1/14, and then negative 10 over 14. 84 over 14 is actually 6. And then I'm going to have 0. This guy, I'm going to divide it out by a 7th. I have a 1, negative 8 over 7. And 14 divided by 7 is 2. Okay, now that I have this matrix complete in reduced row echelon form, I'm going to take my x, my z, equal to 6, my y, the z, equal to 2. I have to assign the value of t to something, so I'm going to let, oops, I'm going to let z equal 7t, and I'm just going to reduce this fraction to 5 over 7. It's just going to help clean things up. All right, so my parametric, my x is 6. Sorry, and this should say 7 t's. I'm assigning something as a value of t. 6 plus 5t. Y equals 2 plus 8t, and z, I said, was t. Okay, give this a try. For all of 6 and all of 7, they become very complicated. Just take your time and check the answers as needed.